Is that a thumb? I'll assume that's a
Yes.
yes. All right, so last time we left off, we were looking at the model for a robotic system, and that's of course in chapter 4. And the idea was is we were going to use some type of vector loop analysis to basically traverse the structure, get to this point, and develop a differential equation for one of these blobs of material. So the idea is that by using this kind of an approach, we can determine the kinematics of the positions of all of those little particles, the velocities of the particles, and then of course, by adding the relative velocity when they come out of the dispenser, we ended up with a differential equation that basically told us how the drop is going to be governed by the gravitational forces and any other external forces, depending upon how fancy we are. So fancy, of course, could mean if this thing happens to be in an environment where we have air drafts, or we have some kind of a fan, or we have an inert gas shield, or anything like that, that might have the ability to determine or induce some type of drag. That could be some external force. We also looked at these external electrical forces, and of course, the external electrical forces are quite interesting. And in fact, let's take a closer look at exactly what's going on there. So the idea is that at this point where we left off is we have some kind of a blob of material. It's been left off by a dispenser. It now is under the forces of gravity. It's under the forces of drag, so there could be drag of some kind that's coming there. We'll call that just simply forces of drag. We'll come back to that in a moment. And each particle may be different, so they may be different masses. So we need to put a little tag there that indicates that that's particle number I, because of course there could be many of these, and there should be many of these if we want to make a structure. So clearly I is going to tell us which one of these particles we're looking at. So let's put a little identifier here that simply indicates that this is particle number I. Down here, way at the bottom, there's some kind of a substrate, and the substrate, of course, is something we're going to try to pattern, and of course, make some kind of a surface. Perhaps maybe we're going to make some kind of a solar panel, or we're going to do some kind of a widget or gadget. So it's some kind of pattern that's complex enough, and we have to get this drop to land at these little different locations and splat properly so that we can make the structure. That's the idea. So the gravitational force is one force, the drag force is another, but then of course, if we're super fancy, and that's not actually that fancy to be able to do it, is we can also then grid up this entire location in terms of electrical pixels. So in fact, we can start to come in here and say, you know what, we'll take this pixel here and we'll electrify it momentarily. We'll electrify this guy momentarily with some kind of a charge. And we'll basically have an electrical force that is going to guide this thing to that location, but just to that pixel one at a time. And we're going to do this over and over again at each of these pixels. And we're going to basically turn them off and on each time, attracting the particles to those locations. That's, of course, the basis of electrohydrodynamic printing. It's also the principle behind Xerox machines and copiers. They're basically all electrostatic printers. These are usually going to be pieces of toner that you'll find in the printer. And in fact, then the target is usually going to be something that looks not flat, but is going to be some kind of a drum that's rotating around while these objects then get latched onto the surface. And then the pieces of paper come along and basically take the particles away. So the idea there, of course, is relatively straightforward. Again, you take the charged material, you take the toner. In fact, I have a good picture of it here in the analysis. That's in fact what a Xerox copier looks like. In fact, in this case, what we have is we have a drum instead of a flat surface. We ablate off certain areas where we have negatively charged surface material. Then those materials are basically charge free. We then dump a bunch of particles, just like a three-dimensional printer, onto the target. They latch onto where there's negative charges, and then you take a piece of paper and you run it through and you make your favorite letter. That, of course, is the basis of electrostatic printing, and of course, is exactly like what we're talking about here with turning pixels on and off in these kinds of objects. The problem is we're going to have to know some physics, which is what is the basis of a significant portion of this class to come later. We need to figure out what, in fact, governs this kind of a type of a force. And that's, of course, going to be, unfortunately, bringing us into the horrible world of Maxwell's equations. And Maxwell's equations, of course, are the equations that govern the electrodynamics of materials. And it's a wonderful and beautiful topic, but it needs a great deal of care. So we need to know a little bit more continuum mechanics before we get there. But if we were going to try to do something naive and we look at basically what's there in packet number 4, essentially what we have is we have some kind of a force. So all we know is we have an object. It has some gravitational pull. It's got a force here that's electrical, I. It has some drag forces here that are called psi drag. And the governing equation is going to be mr double dot of the particle for particle I. So we'll put a little coordinate system here in the corner to tell us, where this guy is. So this guy's over here, and it's particle I. This is equal to the summation of all of the forces. And the summation of the forces in this case is going to be the drag forces due to any kind of surrounding fluid, the gravitational forces, mass times gravity, and then of course, electrical forces. And electrical, I'm being a little bit cavalier here. It should be electromagnetic forces because it could be a possibility that these are using also magnetic inks and things like that. The governing differential equations, of course, or the governing physical forces for the electromagnetic forces are the classical Lorentz force, which is the charge of the object multiplied times the electric field, which we'll call here again external, plus the velocity of the object crossed with the magnetic field as shown here. And again, magnetic field here is in Tesla, and these of course are going to be coulombs or newtons per coulomb for the electrical field. So the product of all of these are going to be forces. So if you want to figure out what the units are, we know that these have to be newtons, right? And these have to be coulombs because that's charge. So therefore the electric field is actually equal to newtons, right, divided by coulombs. And in fact, that's in fact exactly how you back out what the mysterious units are of this electric field. So you can always go back to first principles to understand exactly what these quantities are, because electromagnetism is a very mysterious field in to the human being. It's invisible, number one. That's why it took almost 300 more years for the field of electromagnetics to arise in the form of Maxwell and all of the great scientists of the late 1800s, as opposed to the 1500s when people were starting to develop principles of mechanics. Mechanics, of course, is very tangible and physical. Electromagnetics is the invisible. So, and it took several hundred years more to be able to develop even these simple relationships here that basically on the face of it are quite simple, but were very mysterious until, people like Faraday and Maxwell came along and discovered exactly what they are. The main point we have here is we have some kind of a differential equation, mr double dot I is equal to some function of a bunch of complicated stuff. The positions of the particles, the external electric magnetic fields, the velocity of the particles, you name it, a bunch of stuff. But we have something that comes to the rescue. It's called numerical analysis, which means that simply what we're going to do is we're going to write this as mi r double dot I, which is mi multiplied times vi multiplied times I, which is equal to the forces that are acting on the object. So what I'm going to do there is I'm just going to stick in here a placeholder to put in V here. And what I'm going to do is I'm going to write this as mi vi t plus delta t minus v of I of t divided by delta t is equal to f of v of t I, right? And now I'm going to bring the delta t to the other side. I'm going to bring also then the vi, and I'm left with v of I of t plus delta t is equal to v of I of t plus delta t divided by mi multiplied by f of v of I of t evaluated there, which is pretty simple. Then what I have to do is I only have to take r dot, which is equal to r of t plus delta t of I minus R of I of t divided by delta t equals to V of I of t. And immediately now I have R of t plus delta t of I is equal to R of I plus delta t multiplied by V of I of t. So wonderful, beautiful little equations. We basically have now our velocity equation here. We have our position equation here. And at that point, we do this for I equals 1 all the way to the number of particles n. So as we dump more and more particles out of the system, so if we look at the cartoon of what's going on, as more and more particles come out of the system, the more complicated this analysis is going to become. In other words, each one of these little particles that comes out of the hopper is going to lead to another differential equation that we have on this side. So the problem is that this simulation is only going to grow in complexity as the simulation wears on and on and on. In other words, in the beginning, there's only one drop. And after a few minutes, there's several thousand drops in the system. So depending upon how sophisticated you want to get in your simulation, you could, of course, say once a particle splats onto the surface, I don't care about it, take it out of the system and just keep track of the active particles flying in the air. That's certainly a shortcut that you could use, in particular if you're thinking about trying to do your assignment. So if you're thinking about now how this thing works, let's just go over here and take a quick look. So if we look at the objects that we have, whenever we're dropping a piece of material in one of these kinds of simulations, every time the robot drops a piece of material, that's a differential equation we have to solve. So it's, let me, in fact, give you a better zoom on this thing. Just give me a moment. Let's see. Let me give you a better picture. Yeah, look at this picture here. It's a little bit clearer. So every time you have one of these droplets that comes in fact, and hits, each one of these things that we see a zoom on whenever we drop this guy, one of those particles that comes out of the differential equation is, of course, going to lead to a differential equation we have to solve. So the simplest tool, and the one we're going to use in this class, is basically to have a differential equation of the following form. We're basically going to take the problem here, and we're going to basically allow the particles to be updated by the following time stepping scheme. Now we have a problem. The forces are complex. What I'm going to do is I'm going to leave that up to you guys and Brian to basically work out exactly what those forces look like. But the point is of this is that they're complicated, and they're complicated for a reason. The reason that I'm bringing up what these forces are here now is to illustrate that we don't know much, in fact. And so what we're going to have to do is spend about a week trying to derive and figure out exactly how these forces work. And these are, of course, related to Maxwell's equations. So for what all we know right now is we have some kind of an external electric field. It's given, but in fact, in reality, the external electric field is a function of where the particle is, where the pixel is that's charging that piece of material, how big the charge is of that particle material, where that position is of that particle relative to the pixel, and then we're going to sum up all of the pixels together to basically compute an entire electric field. So here's part of the issue with a simulation like this. Let me just let my cat out. The guy's driving me up the wall. Okay, buddy. All right.
Okay, really?
Yep. Sorry about that. Okay. So the basic idea is the following. Whenever we take the electric field and we have something like that, we essentially are going to take the following type of an approach. So if we take a blob of material, right, we have our pixelations. Every time we have a piece of material that's charged, we're going to turn it on. So turning it on simply means that we have to use Maxwell's equations to basically figure out exactly how big that electric field is. That depends upon many things. That depends upon, number one, how far away the particle is from the object in question. So there's going to be some type of a distance here, r. There's also the normal position vector, which tells us the direction in which this is oriented, this charged piece of material and the charged piece of particle. They're, of course, going to be mutually attractive. So if you think about your basic undergraduate physics, when you had two objects, one is plus and one is minus, there was some type of an attractive force between them. That's the same principle here for one of these pixels in each of the charged objects. So if you look in chapter 4, and you go through the analysis, you have something called activation of point sources. What we do is we figure out exactly how big that electric field is going to be on each of the particles, and that is what provides us with the electric field force that we have there. So part of your assignment is to go through equations 4.11 through 4.14 and ascertain exactly how big that electric field is so that you can put it into your differential equation. Now, part of this also, the assignment, is to understand the basic principles of drag. So let's take a look now at the other drag forces. So keep in mind what we have so far is we have mr double dot, where I is the mass of the object. The position vector is given by r. We've isolated the electromagnetic forces. Those are in fact due to the pixels being charged onto the surface. We have the gravitational force, which I don't think needs any kind of introduction. That's just simply a dead load that is pointing in the direction of gravity. We'll assume that the substrate is at the bottom. So if the substrate is at the bottom here, we basically have gravity pointing downward. So of course, this vector is really going to be 0 minus g times 0, where g is going to be 9.81, the usual value of gravity. Okay, so the idea here is that we've gotten rid of this guy, we've gotten rid of this guy, we only have one more piece, and the one more piece is the drag term. So drag is a dirty business, somewhat complicated, and so if you look in packet number 4 under drag forces, and also in chapter number 4, equations 4.15, it goes through the basic idea of drag, in which I'll explain to you right now. So the basic idea in drag is the following. Whenever we have an object and we have it moving through a fluid, the fluid, of course, is going to move around the object and is going to produce some type of forces on the surface. So the forces on the surface are really the integral of the stress. Okay, so we're going to talk about concepts of stress momentarily in the next week or two, integrated around the body of the object, right? Multiplied times the normal force integrated over the area. So the normal direction, n, is the outward normal to the surface of the object. The multiplication of the stress times the outward normal gives us the force that's acting on there. This is usually called the traction vector. So as we'll see a little bit later, we're going to figure out something called the traction vector. And this traction vector is actually the force per unit area. So the traction vector is the product of the stress times the outward normal. You multiply it times the area A, and we get a little force, delta F. We add up all the delta F's all over the surface of the object. And if we integrate them properly, we get a single force, and that single force is called the drag force. And that's something that I believe all of us as undergraduates have seen. The problem is, this is not an easy thing to ascertain because there's one big, sort of sticking point. How do we get this stress? And the stress, unfortunately, means that if we're thinking about how we might do it in a finite element or a finite difference or some kind of numerical scheme, typically what we have to do is we have to grid up the whole domain where all of this is happening. So imagine now we're putting a big box of grid points of some kind of a computational tool. And we basically have to discretize this blob of material and the surrounding fluid that it's flowing through. That is a daunting problem. We'll look at it a little bit later in the semester, but for us to be able to get an accurate rendition of exactly what the stress fields are around this object is not an easy task. And of course, if you're thinking about putting yourself in the shoes of people in the 1920s and 1930s, when fluid mechanics was really starting to become a field of its own, they needed some kind of an empirical rule to be able to compute what this drag force might be. So along comes equation 4.15. 4.15, basically the idea was the following. So let's take a look at exactly how people reasoned this out. What they said was the following: the drag force that's going to be acting on the object is going to be equal to something called the drag coefficient, CD. It's a function of the shape of the object. So it depends upon the shape of the object. So for example, if it was a sphere with a cross section like this and it's moving through a fluid like this, they have a certain cross-sectional area called the Bluff body constant, which is essentially the cross-section that is facing the direction in which the material or the object is flowing. You have fluids moving around this thing, right? So that's going to be a function of the shape of the material. So it's basically a fudge factor. It's a factor that people empirically measure in a wind tunnel. They put different objects in, they categorize what the drag coefficients are, and they multiply this drag coefficient by the following terms. They simply say that the fluid that is acting around the object, we're going to assume that parameter here, that's the velocity of the fluid that is surrounding the object. However, it's the relative velocity that's important. So if we take the velocity of the drop of material and we take the difference between the drop of material and the fluid here, the relative velocity is given by the absolute value of these of the norm of these two vectors. Now keep in mind, these are vectors. So V of F at any given point is equal to V of Fx, V of Fy, V of Fz. It's a vector. The same thing for the drop of material. The drop of material drop, like shown here, is also a vector. That vector, of course, is given by V of the drop I, x, V of the drop I, y, V of the drop I, z. So it also has a vector value. So each of these things here, the values here are vector valued and vector valued there. So that's the first order of business. This is still a scalar because the norm of the two difference of the vectors is defined as the following. You take the vector V of F minus the vector of the drop. You then take their norm. The norm is going to be equal to V of the fluid, x, minus V of the drop, x, squared, plus V of y of the fluid, minus V of I of the drop, y, plus V of z of the fluid, V of IZ of the fluid, of the drop, again squared, and then all of this junk square root. That is the definition of the norm of the two. So this is a number, and it's a positive number. Now the problem is that we need to give it some directionality because obviously the drag force is a vector. So in fact, we multiply this by, again, the product of V of the fluid minus V of the drop, I. That gives a directionality to this. So we take this term, we multiply it by this term, and then there are several factors that also influence the drag force that people usually calibrate them. And again, one could argue this is all we need, and we're going to just calibrate what the drag coefficient is based upon the material constant. But over several decades, it's become a common agreement that we have a factor of a half. We have the density of the type of fluid that's acting on it. So in this case, if it was air, it would be the density of whatever is here that's flowing around the material. And then also we have, as an additional factor, this is multiplied times the area, that is the cross-sectional area of the object, which is shown there. So if we take all of these features together and we add them up, we basically get something called the drag force. And the drag force is equal to 1/2 rho of the fluid acting around the object, the drag coefficient of the object. So there may be different objects, so we may have several of them, but right now we'll probably assume that all of them have the same shape, that they're spherical. So this will usually be the same number, but again, it depends upon the shape. We have the norm V of F minus V of I of the drop. And then we multiply this by V of F minus V of I of the drop. And then this is all multiplied times the area of the drop itself. And that's the cross-sectional area. So as we can see, there's a little nightmare ensuing. This is a pretty complicated differential equation, because if we now start to think, wait a minute, we're going to have to solve mv dot equals to the drag force, the electromagnetic force, the gravitational force. There's very little chance that we're going to be able to solve this thing analytically, but it's a piece of cake numerically, because again, all of this stuff we're just going to lump together and call F of V. So F of V has many different things hidden inside. It has the difference between the velocity of the fluid, the velocity of the drop, velocity of the fluid, velocity of the drop. You can immediately see this as a nonlinear term. It's quadratic, and it depends upon the absolute value and the direction of the fluid. It also depends upon what you're dropping inside. So depending upon what kind of droplet it is, you get a different drag coefficient. And it also depends upon the fluid itself. That's also a little nightmare, because the fluid, if it starts to change, which it could if we were doing a relatively complex analysis, this would lead to a coupled problem, meaning the object is changing, the fluid that it's surrounding, and the fluid surrounding is changing the object or the dynamics of the object. And this is sometimes called a fluid-solid interaction problem, where basically as the object is moving through and plowing through the fluid, it's producing all kinds of different things like vortices and wakes. So the actual fluid itself that we see here, the density of the fluid, the velocity of the fluid, actually will change due to the presence of the object. So we start to have a coupled differential equation. Now, unfortunately, the differential equations for the fluid are also not easy. The differential equations for the fluid look something like this. They're the divergence of the stress in the fluid plus the body forces that are acting in the fluid. So there could be, for example, gravity, buoyancy, things of that sort. Those are the forces that are acting there. And then you have the density of the fluid itself again, and this is multiplied by the velocity of the fluid, but its time derivative. Now that differential equation, we're going to spend a lot of time on when we derive it relatively carefully, is also coupled now to all of the little objects that are moving through the material. So we have a real problem. These two systems are very strongly coupled, which leads to this moniker here, solid-fluid interaction. This is the solid, and this is the fluid, okay? Now, depending upon how sophisticated we want to be, this could be a relatively complex analysis where we would have the robot moving through a sea of fluid, for example, air, dropping the particles which are affecting the air, which are affecting the robot, and you can start to see this would be a big mess. We've simplified it for you in the first assignment, and in fact, I hope Brian is going to be able to go over that with you tomorrow in the help session. But generally speaking, when we look at the drag coefficients, and I don't want to rewrite them there because they're here on the left-hand side, they're a function of many different things, but the primary thing that they're a function of is the so-called Reynolds number. And if you recall, I explained a little bit last time in class what the Reynolds number is. The Reynolds number is basically as a material is moving through or an object is moving through a fluid, it's basically the inertial forces divided by the frictional forces. And that number is given by a non-dimensional number called the Reynolds number. Now, the Reynolds number is just designed to give you some kind of an empirical feel for how strong the inertial forces are and how strong the frictional forces are. If the material is highly viscous, so it's basically highly viscous, this frictional term is going to be very large, and the fluid is in fact going to work in an extremely smooth and laminar way. That's where we get the so-called terms of laminar flow. If the fluid happens to be a fluid where it's highly turbulent, in other words, we start to have lots of wiggles and we have the material that basically is going to produce a lot of vortices, this is going to be a turbulent problem. And the turbulent problems means that the Reynolds number are going to start to get relatively large. So relatively large Reynolds numbers are going to lead to the drag coefficient changing as a function of it. So the usual parameter that we use to calibrate the drag coefficients are simply to make it as a function of the Reynolds number. So the idea is that CD is some kind of a function of the Reynolds number of the material. So the Reynolds number for a sphere, for example, if we're going to assume these are little spherical objects, is given by the following relationship. It simply says that it's equal to 2 times the radius of the drop, multiplied times the density of the fluid, multiplied times the relative velocity of the fluid and the droplet itself, divided by the viscosity of the fluid. And you can see in the notes how that is worked out. But the main point of this is that as the object becomes bigger, the Reynolds number is bigger. As the surrounding fluid is more dense, the material has a larger Reynolds number. As the relative velocity between the droplet and the fluid becomes bigger, you have a higher Reynolds number. But the one key feature is that in the denominator, we have the viscosity of the fluid. So if the fluid is some light, flitty gas, it's easy to get a highly turbulent flow. However, if the material is some kind of thick molasses-like thing, molten chocolate, oil, whatever, the viscosity of the fluid dominates this, and the Reynolds number becomes relatively low. In the limit, when the Reynolds number is truly super, super tiny, meaning that if I took an object and I dropped a ball inside a vat of extremely viscous fluid and it was just seeping and moving down as it moves downward, that Reynolds number is going to lead to a drag coefficient that's just given by the very simple relationship. It's 24 divided by the Reynolds number. It's in a remarkably simple relationship that comes out from the experiments that people have done over the years. And that's simply because the flow is extremely laminar. It's very, very smooth. It's just moving around the object as it oozes its way down to the bottom here. Now, as the material starts to become highly more turbulent, if I started to shoot this object in, this thing is going to become highly unstable because the fluid is going to induce, or the object is going to induce what we sometimes refer to as vortices. So the swirling and the mixing of the fluid is going to be induced by the fact that the fluid is going to start to have this kind of swirling type behavior. And what you see then is that the drag coefficient is going to start to change as a function of the Reynolds number given by this exponent here. Eventually, as the Reynolds number starts to become really large, the drag coefficient is in fact nearly constant, as you're seeing there in this relationship there. But then it's again for Reynolds numbers that are gigantic, meaning the object is either moving extremely fast, or it's extremely large, or the fluid surrounding it is extremely light and not dense. Whatever those relationships are, the drag coefficient then is given by this formula here. And that's entirely a curve fit, by the way. That's a famous curve fit done by Hermann Schlichting in the middle of the 20th century. So it's a very famous set of experiments that he did in wind tunnels. Finally, as the Reynolds number becomes nearly infinite, meaning this thing is really, trucking through this material, the drag coefficient again becomes nearly constant at 0.18. So main point here is that the drag coefficient as a function of the Reynolds number is something nutty. So it's going to go all over the place. So this thing is what's lurking in your differential equation. You have a differential equation where the sum of the loading coefficients, the drag coefficients here, are very complicated in terms of inside here, where you have the differential equation, you basically have the gravitational force, the electrical force, and now the drag coefficient that's there is given by this relationship here. Now, in this relationship, as you can see, the drag coefficient is in fact this complicated relationship that we have shown there, and that's given by this piecewise continuous curve that you see, shown here. Let me erase all the crap that's all over this thing.
Professor Zohdi, we have some questions in the
Absolutely.
comments.
Just give me one moment. Let me finish the train of thoughts, and we will then go directly to the question. So up until this point, what we have is summary, complicated differential equation, but numerical analysis to the rescue that looks something like this that we're going to solve numerically. Now, unfortunately, that's half of the problem. We now have to deal with thermo. So thermo is going to be the other thing that we're going to have to contend with. But before that, please go ahead, ask a question. I'm all ears.
Hi. So a few slides ago, you were talking about the drag force and how it's a challenging thing to take a derivative of. Yes. But if it seems like our end goal is the acceleration, the v dot. So why are we concerned with taking a derivative of the force in the first place rather than just dividing by mass?
Well, so the problem is that we have to get the position of the objects. And that's really the real dilemma. That you're absolutely correct. If we just wanted to get the forces, we could do that. The problem is that, let me expand it a bit here, and I can get to the point here. That if we're looking at the differential equation for the mass, just give me one moment. So if we're looking at exactly the forces that are acting on the piece of material, you're absolutely right, it's the acceleration. But the problem is that we need to integrate that to be able to get where the particle is and where it's going to land. So for us to be able to track where the particle is, we unfortunately have to integrate this differential equation, which means we're going to have to discretize the velocity, and then we're going to have to discretize the velocity again, or integrate the velocity again to get the position. So we first have to take the derivative of the velocity, get its position, discretize it in terms of velocity there, then get the position by again discretizing it one more time. And then we basically get a relationship that says the drag coefficient, the gravitational force, the electrical forces, that gives us the velocity at any given moment in time. But then we integrate it again and we get the position at any given moment of time. The reason that we have to integrate that, Lena, is that we also, these terms here, they keep changing as a function of time. So if it would have been okay, we may have gotten away with not having to integrate it had the velocity not been there and had the drag terms not depended upon the velocity, but they unfortunately are going to update the values here, which means they also change the positions. Now, what we're going to see in just a moment is we're going to have one other actor come into the system, and the other actor in the system is we're going to solve the thermomechanics equation, which means that we're going to have a differential equation that tells us how hot these objects are as they're flying through the air, and how hot are they when they land on the substrate.
Okay, thank you. Yes, it does. Sure. Thank you.
Any other questions? Anything? Now's the time to blurt it out. I see in the chat. Why would we consider taking acceleration? Daniel, forces relative to velocity. I would think no, because the scalar equation is v squared. That's good. We've already done that. We're normalizing it. The kitty cat, that's correct. Any other questions before I plow further? Don't worry, we'll have time at the end of lecture. We'll have some more Q&A, but anything right now? All right, then let's continue. So the main idea here is that at this point, all we've gotten so far is the actual state that tells us where the objects are in some three-dimensional reference frame, and we're tracking where they land. The problem is that when they land, we need to know how hot they are, and we need to know how long they're going to cool down, and how soft and mushy they are, how they will splat, and of course, all of that is dictated by the wonderful world of heat transfer. So in the wonderful world of heat transfer, we basically have the following situation. We have an object, and that object is going to exchange heat with its surroundings. So the heat might go in and out. It also may have heat due to the drag forces of terms. It may also have heat because initially when it gets pushed out of the extruder, it's already hot. So our problem is that how hot is this thing going to be when it hits the target way down here? So the governing differential equation for this is that we take the mass of that same object. So again, we have the mass of one of those blobs of materials. We have something called the heat capacity of the material. So I'll put a line through here just to indicate that it is not necessarily the drag coefficient. It is not, of course, the drag coefficient, but it's just simply a property of the material. And that's how much heat the material can retain. So if you remember what heat capacity is, it's exactly as the word indicates. It's the capacity of that type of material to retain heat. I'm going to use the symbol theta for the temperature so we don't confuse it with time or T or anything else. And we're going to take the derivative of that. That is the power that is going in and out of one of these blobs of material. So this is a very coarse representation of all of the events that are going on for a blob of material. What we're going to find out later is we're going to do a hyper careful analysis of a blob of material where we take into account everything that's going in and out, including even its changes in the geometry as it starts to splat and hit other different objects and so forth. Right now, keeping with our simple first model for our first assignment, we're just going to assume this is some kind of a spherical blob. And the spherical blob doesn't change its shape until it hits and splats, and then it becomes a flat pancake. Of course, that is a gross simplification of the nightmare that is going to occur when these materials actually splat and hit a surface. Of course, when that happens, typically what we'll see, and then let's look at a simulation of exactly what occurs there, is when one of these blobs of materials hits, it goes through some very nightmarish set of events. It basically goes through an event where right when it comes out of the dispenser, it's usually a long, thin strand of material. That strand of material then will congeal because it has been constrained by the walls and now it's electrically charged. The electrical charge is so strong it'll pull the material apart. Then as it hits the target, it's of course starts to change its shape. It melds with the other thing and then it splats. We're going to make gross simplifications and say, you know what, we don't know anything. This is just a blob of material. So that is still our little point mass that we've been including in the analysis here. But what we're going to see later on and starting on Thursday and also all of next week and probably for the next 2 to 3 weeks, we're going to take into account all of the geometrical changes in these materials when we start to do a more careful analysis. And a more careful analysis, as we are starting to look in forward after this starter example, is basically an analysis of, sorry, scrolling a little bit, is the analysis of the continuum, which is really the meat of this class. Basically, we're going to take a blob of material and we're going to do a careful analysis of how things stretch, how things strain, how they fracture, how they deform as a function of the loads that are acting on the body, and then also as a function of how hot the object is at the same time. So that's where this assignment is leading us to the conclusion that as wonderful as that simple assignment is, it makes some pretty gross simplifications. So to polish off the last simple gross simplifications, just like we had for the summation of forces, we're going to have the summation of course, in this case, the analogy is heat fluxes. So what are the things that are happening around one of these little blobs of material? Well, let's take a look. So if I take the object, and I'll just erase this sketch below it, and let's draw the little blob of material. So we've all learned in an undergraduate class in thermodynamics or physics, we do a control volume. We isolate the object and we ask how much is going out and how much is going in, and then how much is being stored, right? Those are the three things. So stored is obviously going to equal to what? Is going to equal to out minus in, right? So the rate of how much is stored is out minus into, okay? Now, depending upon how sophisticated we get, we can come up with basically a simple analysis like this. It simply says the amount stored inside That's given by this term here. So this term is basically the amount of mass that's inside, the heat capacity of what's inside, and then the rate of change of the temperature is equal to all of the things that are fluxing in and out of that object. Okay, that's the basic premise behind these relatively simple differential equations. So if you look at the analysis and you look on the left-hand side of the panels, we have 4 different possible terms that can be fluxing in and out. And let's take a closer look of exactly what those look like. So I take the object. The first thing that, might influence whether this thing is going to have some heat exchange is perhaps it's hitting the wall. So we might have some kind of conductive energy, we'll call that Q of I, that is conducting when the object makes contact with something else. Now, it could also be making contact with another one of these blobs, right? So we can, of course, take that into account. But nonetheless, whatever it is, it's something that's basically making contact with the body and is leading to this term here, the so-called conductive term, right? Another type of physics is the fact that when we have a flow of a fluid or some kind of material around an object, little parcels of heat that are sitting there on the surface are basically lifted off and are convected and carried away. You can think of them as little embers, if you like, little pieces of energy are on the surface of this object. They're hot. They're basically then carried away. That's given by the so-called convective type term. So let's call this thing here convective type term. So I'll call that H of C of I. Okay, so convection. We have conduction. Then we have also what we sometimes refer to as black body radiation. So basically what happens is as the material gets glowing hot, it radiates heat, much like a sun or some kind of a resistive heating element. And that resistive heating element or that radiative type of heat, we're called that H of Ri, and that is radiation. Okay. Finally, we have the potential that because this thing is moving through a fluid and the fluid is moving around this object in all kinds of different directions, it may also have something that we refer to as drag heating. And drag heating, we're going to call that again by the symbol here, H of drag I. So 4 of these rascals exist. We have convection, we have conduction, we have drag, and we have radiation. So those 4 terms, depending upon how fancy we get, are going to also feed into this differential equation. For the time being, we're just going to say this is equal to mi, c of I, theta dot of I, and then we're going to have conduction plus convection plus radiation plus drag. And we're going to call all this junk over here. I think I used the symbol. Let me see what I called it. Just give me a moment. I'll call it F of theta I. Now, F of theta I, it's important to understand. In fact, it's not a vector. Sorry about that. It's a function of itself, meaning that over here, we have the rate of change. And over here, depending upon what these values are, they're all going to contribute to this loading type term. And they're all a function of the temperature of the object. So depending upon the temperature of the object, that will of course change how much energy is conducted away. Depending upon the temperature of the object, that tells us how much convective energy is going to be moved away. Depending upon the temperature of the object, it tells us how much heat it's going to radiate away and how much it's actually going to absorb by its surroundings as well. And then finally, depending upon the temperature, it's going to tell us what the drag heating is going to be when the material is moving around this object as well. So we have some tools. We know one thing. We have one trick. We have theta of I of t is equal to t plus, sorry, excuse me about that. Theta of I is equal to approximately theta of t plus delta t, I, minus theta of I of t divided by delta t. That's the approximation of this term there. We're going to then multiply everything on this side. So we stick that into the differential equation, m of I, c of I, theta of I, t of delta t. minus theta of I of t divided by delta t is equal to the function of theta as a function of t. We bring the delta t to the other side, we bring the theta I of the other side, we divide by the mc of I, and what we get is theta of I of t plus delta t is equal to theta of I of t plus delta t divided by mici multiplied by f of theta of I of t, which is the term we have here on the other side of the equation. So again, if we look at the differential equation here, written nice and neat, there are complicated expressions for the convection, for the conduction, for the heat radiation, and then also for the drag terms. You should look at those in chapter 4 so that you can solve the assignment. They're very physical and simple principles in describing them. But the bottom line and the main point of that assignment is to simply say, this is a complicated thing, but we have now the following possible numerical tools. We have number 1, we have mi v of I equals some type of forces. We'll call this for the mechanics times v of I. And then we also have mi c of I, theta dot of I equals f of the thermo, as a function of theta I of the thermo. Notice a couple of important things here. Number 1, scalar. This is not a multi-dimensional equation, even though theta might be a function of x, y, and z, it's still scalar valued. Now, that's going to be a recurring theme all the time in this class, because this object, even though it might be flowing through space, at any given moment of time, there's only one value of the temperature for this little blob of material. There's not 3. However, so we know theta of I. However, how many values of the velocity do we have? Well, the velocity is a vector valued velocity. It's going to be v of I of x, v of I of y, v of I of z. It's also r of I of x, r of I of y, and r of I of z. So there's actually 6 variables associated with the mechanics of this and 1 variable for the temperature. So at any given time, you need to drag around 7 variables with each of the blobs of materials. Okay, these are sometimes referred to as state variables because they basically tell us the state of the object, which requires, in this case, 7 terms. Sometimes you'll see it in some of the literature, they'll be called history variables. Okay, so they're telling you basically what the history is of the object in question. So as you're starting to encode your assignment, keep in mind that you need a 7x1 vector that is going to tag what each of these particles is doing. So if I'm thinking about how the simulation is going to look, and I've got lots of these little objects moving around in space, every one of these things basically has a vector that is associated with this, which is theta of, for example, object number, we'll call this number 5, number 4, number 3, number 2, number 1. We'll erase this one here. Let's suppose there are 5 objects here at this given moment in time. So if I look at object number 5, I basically have something that says it's theta of 5, velocity of 5x, velocity of 5y, velocity of 5z, position of x of 5, position y of 5, and position of 5z. Okay, and I need one of these, history or state variables for every single one of these objects. The way I'm going to get them is I'm going to solve these differential equations. How do I solve the differential equations? In summary, that is that we take v of t plus delta t of I is equal to v of I of t plus delta t divided by mi multiplied times f of v of t of I. So at any given moment in time, You know this because this is the previous time. You know the delta t because you set it. You know the mass because you know the object. You know the previous velocity. That means you can update the value and get v of t plus delta t. Also at the same time, you have r of t plus delta t of that object is equal to r of I of t plus delta t times v of I of t. Be careful. Put a big star by this. This is not, by the way, a dot, so let me get the sloppiness out. This is v of I of t, not this. Oftentimes, the first mistake people make in the coding of this is say, well, I just computed the velocity, therefore I'll stick it over here to compute the position. That's a potential other kind of scheme. Many fancy other schemes will use the current value of the velocity to try to get the value of the position. But in the explicit time stepping scheme, which is the one that we are using here, it's all known stuff on the other side. So this is known. So everything on the right-hand side here are known things. The V's, the delta T's, the positions, the masses, all known things. Okay. Now, for the mass times the heat capacity, same issue. We again take the derivative. We take F of the thermo. We have theta I of T, and that immediately gives us also a theta I of T plus delta T equals theta I plus delta T mi ci f of theta of t I, and we're done. So for every one of these objects in the system, I equals 5, I equals 4, I equals 3, I equals 2, I equals 1. We have to keep track of both the theta and the velocity and the position. So in summary, what do we do with the thing we just generated here? Well, we use this then in conjunction with many other empirical relationships. So for example, depending upon how sophisticated we want to get, we can start to describe, for example, the fluid action as a function of the Reynolds number and something called the Nusselt number. That tells us how much energy gets convected away. I leave that up to you to look at that empirical relationship. It's a hokey, funky little relationship that really is just simply a holdover from the 1950s, 60s, and 70s, although it is used continuously in the literature. Most of the time people use finite elements or finite differences to compute that, but nonetheless, what people do is they figure out what the so-called Nusselt number is, which is a ratio of convection to conduction, and that dictates how much energy is convected away. For our purposes, this is just an empirical relationship. Same thing for the effective conductivity. So if we start to think about what is the effective conductivity of one of these blobs? So right now, these blobs, if they start to encounter some kind of an object, the first question is how much heat actually gets propagated in and out. Well, that depends upon the thermal conductivity of the material. Now, our problem is that the thermal conductivity is a point mass value. In other words, if I'm looking at an object and I'm looking at a piece of material, there's a value of the conductivity at this location here. There's a value of the conductivity at this location. There's a value of the conductivity at this location. Every material point has a different value of the conductivity. Now, our problem is that when we start to look at these blobs of material, they're a giant messy mixture of all kinds of stuff together. In other words, when we're looking at the pictures of this stuff and we're treating this as one big blob, it's nothing but one big blob. It's a mixture of all kinds of different materials. So usually what people do is they come up with what they call effective medium theories. Effective medium theories basically say the following: if you take an object, and that object is a mixture of many different things, these dark particles, light particles, dark particles of different sizes, all that kind of stuff. That entire mixture, we replace it with a single homogeneous value of what the properties are. So here's the problem. This mixture, there's a conductivity of this mysterious interstitial material. So that's called that interstitial. There's a value of this particle. There's a value for this particle. And each one of these are completely different as we're moving through the mixture of stuff. Now, if we really tried to do a detailed analysis of this drop, taking in all of this stuff into account, we'll be here for 50 years. Because this is a complicated, messy blob of material. And as you can imagine, when you're looking at this kind of a simulation here, this is going to be a big mess. So our first foray into this is to simply say, you know what, is there some kind of effective theory that could basically replace all of those little pieces here by one simple effective medium? And the answer is yes. This is a well-worn topic of so-called effective medium theories. So effective medium theories, what they basically do is they say, look, if you need to get an overall parameter, like the effective conductivity of this blob of materials, let's say it's a function of, for example, the particles of the first kind, the particles of the second kind, the particles of the third kind, the particles of the fourth kind, and they come up with all of these different rules called mixture rules. So mixture rules basically take all of the different mess that is comprising an object, and they come up with rules that tell you what the effective media are. We're going to spend a lot of time on that towards the middle of the semester, because it's an important and essential piece of understanding how the properties of materials change as a function of their composition. This is sometimes called the world of micro, macro mechanics. And micro-macro mechanics attempts to do the following. It attempts to determine what exactly are these kinds of laws that give you the ability to do this kind of effective medium theories, but based upon some very solid, reasonable physical reasoning. There are some definite reasons why we can get away with lots of these types of empirical relationships, but that requires a little bit more math, and we'll get to that towards the middle of the semester. The main point I wanted to make in this is that when we look at this kind of a relationship here, let me go back to the notes, you will see that in the relationship for the effective medium theories, equations 4.26, they give you formulas for what those are. We'll come back to exactly how we derive those towards the middle of the semester, but for the purposes of your assignment, you're simply just to use them to get effective medium representations for all of the blobs of material that occur in the system. So the bottom line at the end of the day is we integrate for the velocity in equations 4.33, we integrate for the temperatures in equations 4.35, and we basically solve the system. So if we start to think about what the algorithm is for your system to work, let's basically take a look. So if we're writing basically the relationship, we compute the robot position at any given moment in time. So let me come here on the side and draw a little sketch while we're talking about that. So the sketch basically is I have the object, the robot, and at any given moment in time, it's at some location here, and it lays an egg in the air. That's the little drop, okay? So compute the robot position at time t. That tells you that an object is coming out of the system. There, of course, are pre-existing objects that have come out already from the previous time steps, but at a given time step, you have one of these things coming out of the hopper, okay? So the things that are coming out of the hopper, we're basically given by these values here. We set a counter. And the very first part of the simulation, the very first one that comes out, that's I equals to 1. That's the first particle. I equal 2, second particle, I equal 3, third particle, and following. So as the simulation is wearing on and on and on, you have more and more particles that you have to keep track of. So clearly, if you start to run this thing for a long period of time and you're going to build a sand castle, and you're starting to think of how many particles potentially are in grains of sand, this could be also, if you're not careful, a huge calculation. So we have to basically keep metering how many particles we're going to use in the system when we do this. The bottom line is we compute the position and the temperature for each of the lumped masses. We increment then the robot forward in time. So imagine now the robot has moved here. And now it drops a new egg. So now we have the previous values of the particles. We now have the new system of the particles. And then the robot again does something else. It drops another set of particles. And again, we have these values here. But in doing so, what we're able to do is we're able to track how the particles move. We're able to track what the robot does. And then we come back to the very premise at the beginning of the semester of this class, which is how do we optimize the system? So now let's go back and think about, we have a tool. This tool basically gives us the ability to track how these objects move in time. We can integrate them forward. And if you encode this properly in a pretty fast language, for example, I use Fortran, but of course you use MATLAB or Python or C or something like that. This entire simulation with a couple of thousand drops takes about 1/30th of a second. So in your assignment, your robot should be moving pretty quickly. 1/30th would probably be extreme unless you're an extremely good coder with a very fast machine and using a high-level programming language. It might take you 5 seconds, 1 second. It's got to be reasonably fast because you want to do this a couple of hundred times to be able to do what we want to do next, which is we would like to take the system, integrate it forward in time, and see what the results are of this thing doing some kind of a job. Our problem is now we come back to the very basic premise that we talked about last week. My boss comes along and basically says, okay, make this pattern. I've given you this robot. I took it out of the box. It's sitting there on the shelf. You program, you tell me what the robot needs to do to basically lay all of these particles in a figure 8 and make this object. Now, you can do it the hard way, which means sit there, trial and error, and really grind this robot into the ground, trying every possible combo, or you can pre-program this thing with what we learned over the last 2 to 3 lectures. So first object is, I need to make this pattern. Now the problem is my very first computational foray into this is it drops the objects and it drops them all over the place. It doesn't even get close. It makes a pattern that looks maybe something like that, okay? So what I'm gonna do is I'm gonna take the difference between pattern 1, so I'll look at it flat, I have this figure 8, and my other pattern, which is, some crazy thing that went all over the place like this. I'm gonna take the difference between these 2 curves, and I'm gonna give this thing a score, okay? The score is basically gonna drive the genetic algorithm that we introduced all of last week. So the genetic algorithm, again, is gonna be doing the following. We're gonna take the designs, so let's now do the algorithm. I'm gonna take the designs, and I'm gonna put all the parameters in the system, and whatever Brian gave you as the free parameters, these are all the free parameters in the system, okay? I'm now going to feed the parameters into the model for the robot. So this is where the good programming comes in. I put these parameters into the robot, and it pops out some kind of a pattern, okay?
Professor Zohdi, could you show your notebook?
Oh, I'm sorry about that. Pardon me. Yeah. So it makes a pattern that basically is going to be of some shape like this. Now, my second question then is, okay, I'm going to give this thing a score. So the score is going to be what I got, what I want. I'm going to take the norm of that divided by what I want to make it non-dimensional, okay? This is going to be the value of pi, or cost function, when I put in these design parameters here, shown here pictorially as this kind of DNA strand. Of course, the DNA strand, we've given it a name, lambda, and is the set of design parameters as shown there. Keep in mind, the vector valued aspects of this are exactly the vector valued aspects of lambda, which is lambda 1, lambda 2, all the way down to lambda n, number of design variables, and I here will be the design number. Okay, that's step 1, is I put in all of these guesses and I see how well they did. So I have to basically Step one, generate the population. So generate populations. So I don't know, pick a number, take I equals 1 to 100 of these populations. So if you're thinking about a Petri dish, your Petri dish has 100 of these weird little designs swimming inside, okay? Step two, evaluate all of those designs. So this is the hard part that we spent the last 2 lectures on, is we're going to solve some differential equations. So our differential equations are going to basically boil down to the ones that we're seeing here. We have the differential equation for number 1 for the position of the objects. Then we have also the differential equation that tells us for the thermomechanics. So deep down inside of here, we look at the equations here, we've got some kind of a solver that's solving mv dot equals et cetera, and mc theta dot equals et cetera here. So this thing, it better be fast. Because if it's slow, this is where you're going to get nailed. It's basically going to be that this thing takes 5 minutes each time you're going to do a run. And if you've got to do 500, 600, 700 runs, your code will take forever. So please spend a lot of time making this as fast as possible, because this is the secret sauce. Okay, so once you do this, you get a score for each one of those designs, and you then rank them. So step 3, rank the lambdas. Okay, step 4, breed the winners. So you basically take your best designs, and we went through this last week, and you combine them and you produce hybrid designs or children, okay? So these hybrid designs, basically, in the algorithm we picked, again, it's a subject of matter of taste, we decided we're gonna make 2 children for 2 parents, okay? Another algorithm might make 8 children for 2 parents, or might make 1 child for 2 parents. We've decided 2 for 2, okay? So we're gonna produce 2 children for 2 parents, 2 children, 2 parents, and then we're going to eliminate all bad performers in the system. So that means that if I'm looking at my Petri dish and I've created these parents, and now I'm going to come along and create children. So let me make the children, I'll make them wiggly looking. So the children are the wiggly guys, right? And those are produced only from the parents that did well. I now have to come along here and kill off the ones that I did not mate and weren't doing well, whatever those are, and take them out of the system. So they're going to be taken out. And I'm going to put new stuff in that is completely random, again, in the design space, and add those to the children and the parents. So the children and the parents, I'm going to keep them. So let me put a little marker here. I'm going to keep the parents that were good performance. Obviously, I'm going to keep the children because I just generated them. So I'm going to keep all those things. And I'm going to throw away the ones that are bad performing. So let's assume I keep K parents, keep, right? And K children, keep. And that leaves me with 2K. If my total population was, call it S, that's the total, I have to take S, subtract away 2K, right? And then determine how many I need to add into the system. So let's take a look. I've got a total of S population. I'm going to keep 2 parents. So I'm going to keep K parents. That's the total number of parents, plus K children, okay? And if I take S and I subtract away K and I subtract away K, what's left is S minus 2K. Those things are all the things that I'm going to have to add into the system to make the system stay as a population of S. So I have to throw away how many? If I had 100, I think we've discussed this last time, and if I keep the top 10 parents, I keep the top 10 children, I keep the parents. That's originally going to be 90 that were there. 90 of the bad performers are out of the system, so I'm going to eliminate the 90 low performers. I have 10 new ones that were generated by children. Then I need a total of 80 to add into that to keep the population at 100. After that, I repeat the process over and over again, and I create the population, and I do it recursively. It's just now we have something physical to sink our teeth into. That's basically the robotic propagation of this material. So if you look at the end of the chapter in this packet number 4, it generates exactly the algorithm you need from start to finish, starting from the distribution of the particles, the thermomechanics of the particles, the score of the particles for the machine learning algorithm, and then finally the algorithm of population generation, population evaluation, population or mating to produce the children, gene elimination, generation of new genes, and keep repeating this procedure over and over. So at this point, I want you to show me what you can do, but that's a big bulk of what we wanted to get over with. Now, here's the problem with this kind of an analysis. There were gross simplifications. You know, the electric field, the deformation of the objects, the temperature of the objects. And so what we want to do is we want to dig deeper now in keeping with a graduate level class. We want to understand now a little bit deeper what the heck is going on. So what we're going to do is we're going to walk it back and start to ask the following question. How do we actually describe how these materials are behaving? They're complicated. They're getting the heck beat out of them. Their temperature, they're being melted. They're being potentially even zapped with lasers. We haven't even gotten there. So that's where we're going to start. So chapter 5 starts to do a hyper careful analysis of deformation, strain, stress. Some of it you may have seen as an undergraduate, if you've had an undergraduate class in mechanics or strength of materials or statics. But most of it would be hard to believe that you've seen it unless you've had a specialized class as an elective, for example, a class like 185 in the mechanical engineering department. There's a class called 185. It's undergraduate continuing mechanics. It's also, I think, cross-listed also as 287. It's cross-listed as well as a graduate class. It's a phenomenal class. It goes into extreme depth. We're going to do somewhat of a lighter version of that so that we can get a handle on what the mechanics are. And then we're going to solve even more complicated problems, but with the feeling that we know first, macroscopically, what we're after, which is, for example, a robot or any kind of complicated manufacturing system. And we know much more about the mechanical behavior of the materials and how those behave. And those combined together leads us to a really dynamic duo in terms of something that we can actually really feel comfortable with in terms of describing these manufacturing processes in an advanced way. So we have a couple of minutes for questions if you'd like to ask, or we can sign off. So I'm available if you want to ask some questions. I'll take that as a silent, I'm tired. Rejuvenate, go watch something good on Netflix, relax, and then go back and code this assignment. Lena, do you have a question?
Maybe. So in the random generation,
Yes.
would it make sense? So the random number generator, we can kind of give it a parameter of like, do we like what decimal place we want it to get into?
Yes.
And yeah, so would it make sense that every generation, maybe we let it go to a further out one, or maybe that would put us into a bad sinkhole that's like not actually the
gotta
best?
be careful. Yeah, don't do that. So what you should do is the best way I've found to do these random number generators are you have a parameter that you need to randomly generate. Let's call it component number 1 of this genetic string. Let's suppose it's this one. and it lives between lambda 1 plus, the maximum it can be, and lambda 1 minus, the smallest it can be. So what I'm going to do is I'm going to call my random number generator. And in Fortran, in MATLAB, there's one that basically says, you know what, I'm going to generate a number between 1 and 0. Okay. Now what I'm going to do is I'm going to take lambda 1 minus, and I'm going to add that random number multiplied by lambda 1 plus minus lambda 1 minus. Now, what's going to happen if I do that? If I take the difference between the two, let's suppose the random number was a value,
Professor,
for
we can't
example.
see your notepad.
Oh, I'm sorry about that. Excuse me. Let me put it back here. Okay. So if I take the difference between the upper bound and the lower bound of where this design parameter is for the very first component of this genetic string, and I start here at the baseline value of the smallest one, how big of a value do I need to add to that to basically make this thing, the maximum? So if R was equal to 1, and I have a random number generator that generates any number between 0 and 1, what is the value of my new parameter here that I've generated called lambda I equals lambda 1. If R is equal to 1, this becomes lambda 1 minus plus 1 times lambda 1 plus minus lambda 1 minus, which equals to lambda 1 plus. So just with a single number R, I'm able to generate anything that slides in between the maximum value, lambda 1 minus, and lambda 1 plus, that in between those two variables, I start here, I start with the lower bound, add the random number that goes between 0 and 1, and it slides and basically figures out any possible value between the max and the min. So what I do is I do this for all of the different variables, for this variable, for this variable, for this variable, with the following simple algorithm. I take the lower bound, I add a random number generator multiplied times the upper bound minus the lower bound. And I do this for all of the variables, lambda 2, different random numbers, so call this R hat, lambda plus number 2 minus lambda minus, number 2. And I do this for all the design variables all the way from lambda n minus random number generator number n, that's just a different value. And I do this for n plus minus lambda n minus. The main point is I generate these random numbers here, right? They always are going to live between 1 and 0, but by adding them to my lower bound and multiplying them by the difference between the lower bound and the upper bound, I can create any random number in between the upper bound and the lower bound, just with a simple random number generator that basically always varies something between 0 and 1. Does that answer your question, Lena?
Yes, thank you.
Okay. That's the one I found the most effective and is very simple to encode, because almost all the random number generators usually give you something between 0 and 1. That's usually the default. You need to make sure, by the way, so check whatever kind of random number generator you have in your computing language, because depending upon the computing language, sometimes it's different. But the main point is that with that simple random number generator, then you can just scale it by multiplying by the gap and adding it to the lower bound. Any other questions?
The professor?
Yes.
Well, I actually asked this question before after class. And how do we keep the arms three always horizontal?
So that's a thing. I mean, I don't know whether you were sure asking that in terms of practice or just as a mathematical exercise. All you have to do is always keep this thing to remain horizontal in the codes. In other words, as you're doing your analysis, this thing is just going to simply be moving up and down. You have to make sure that it's always remaining horizontal by simply implementing it and forcing it. So in other words, as your object, your robot is moving around, you stipulate in the algorithm that this thing, the plane here, is always going to remain horizontal. Now, the way that's physically done is typically what will happen is the arm here is a ball and socket type of joint as opposed to a pin joint that is shown here. So let's suppose this was a pin joint. This is what is a ball and socket joint, for example, much like what you have in your hip. So imagine if this is the object and it has a sliding thing that's sliding around in here, I'm going to simply have the controller, the robot, basically have a servo that says, regardless of where this arm is moving, this thing is going to constantly keep readjusting, that is always remaining in the horizontal plane. That was just to make things a little bit simpler for you. Of course, if we could have just made the arm move up and down with it as well, but we've basically turned it in sort of like a helicopter blade where as the object is moving, this thing is always remaining in the horizontal plane. And that's of course done with what we call a universal joint. And these are pin joints shown here. So does that answer your question, Boyan?
Oh, okay, thank you.
Okay. Any other questions? Well, then have a good evening, and I will see you on Thursday. Please try to attend Brian's session because he'll give you all kinds of hints. But Brian, please, if you could upload the recording, I'd appreciate it. And I'll see you all Thursday.